All right, so today we're going to first discuss the solutions for assignment 1, and then we'll complete the proof of Tude's theorem. And if we still have time, we're going to discuss another problem related to matching, okay? That is stable matching. But yeah, let's see if we have time for stable matching. So let's start with the solution for assignment 1, okay? Okay, so the first problem is to determine whether this degree sequence is graphical or not. Okay, so we've discussed an algorithm that can determine whether a given degree sequence is graphical or not. And the idea is that in each round, we're going to pick a vertex. And we're going to add some edges to that vertex and then update the degree sequence. And the key point is that when we add edges, we have to make sure that these edges are connected to the vertices with the largest degrees. Okay, that's the only key point. So let's first, since there are 8 degrees, right? Okay, 8 degrees, so we create 8 vertices. Okay. So these numbers indicate these vertices target degrees. Okay, so we want to make sure that for this vertex, we can add 4 edges to it. Okay. All right, so let's just apply the algorithm. So let's say we first pick this vertex, okay? So since this vertex has a target degree of 3, we have to add 3 edges. And these 3 edges must be connected to the vertices with the highest degrees. Therefore, we can choose these 3 vertices, okay? Because they have the largest degrees. And then we just update the degree sequence. Okay, and repeat. Okay. So say in the next round we pick this vertex of degree 1. Okay, so we have to add 1 edge. And this edge must be connected to the highest degree vertex. So for example, this one. Okay. Okay, and say let's pick this guy. So it has a degree of 2. So we have to find the 2 largest degree vertices. So we have to choose this one because it has the highest degree, degree 3. And then we can choose this one, okay? Okay, so now the remaining degrees are 2, 2, 2, 1, 1, okay? If you want, you can still apply the algorithm, but whenever you see a bunch of 2s and 2 1s, you know that this is actually a path, okay? Or it can be realized by a path, because in a path, only the 2 endpoints have degree 1, okay? And all the internal vertices have degree 2, okay? So we can just add edges and make sure that these edges form a path. Okay. So I think the trick here is that when the degrees are small enough, say in this case, there are lots of 2s and only 2 1s, then you can realize by a path. Or say when all degrees are 2. And if all degrees are 2, you can realize it by a cycle, right? Because in a cycle, every vertex have degree 2. Or if all degrees are 1, then you know that these are just a set of edges, okay? Because in every edge, the degree is 1, okay? Or it's like a matching, okay? So if you have a matching, then all the saturated vertices have degree 1, okay? So yeah, when the degrees are small enough, you don't have to apply the algorithm until all degrees become 0, okay? There are some shortcuts. So anyways, for this question, the degree sequence is graphical because this graph realizes the degree sequence. Okay. Okay, so the next problem is related to maximum matching in bipolar graphs. Okay. So this is actually a tree, okay, and every tree is a bipolar graph because by definition a bipolar graph is a graph that has no arc cycle. And in a tree, you cannot have arc cycle because you don't have any cycle, in fact, okay? So if you do not have cycles, then you do not have arc cycles, which implies the graph is a bipolar graph. So for the first subproblem, you have to identify the two pairwise sets, okay? X and Y. So this is easy. So okay, so we can just choose any vertex, say vertex A, and let's just assign A to the set X. Then you know that the neighbors of A must be in Y. So that's why I put B and C in set Y. So this is set X, and this is set Y. Okay? And for neighbors of B and C, since B and C are in set Y, so the neighbors must be in X. Okay? And so on. So yeah, it's that easy. Okay. Okay. So the next one is to show that matching is given matching AC and BE. Okay. So let me first add all the edges. Okay. So here now we have all the edges, and we want to consider this matching, AC and BE. Okay. So this is a matching, and what we want to do is to show that this matching is a maximal matching, okay? Not maximum, just maximal. So to show that the matching is maximal, all you have to do is to show that you cannot add any more edge to this matching, okay? So yeah, it is easy to check. For example, if you consider this edge A and B, okay, then because A and B, they are already saturated, so you cannot add it to the matching. Similarly for like these two edges between E and H and I, because E is already saturated, so you cannot add these two edges. So basically, all you have to do is to show that every edge, if you consider the endpoint has already been saturated by the matching. So it's a maximal matching. Okay. And the next one is to find augmenting path, okay? And you also have to identify the set S and T, okay? All right, so let's start with S. So initially, S contains all the unsaturated vertices. So in this case, we have 3 unsaturated vertices, D, F, and G. So they are the initial vertices in the set S, okay? And then we're going to just extend this alternating path from these 3 vertices, okay? Until we find a vertex in Y that is not saturated, okay? So for example, we can start with this vertex G, and then we use this H, which is not in the matching, to reach the vertex C. So C is in T because we can reach it using an alternating path. And we have to check whether C is saturated or not. So in this case, C is saturated. So we can use this H between A and C to reach A, okay? And yeah, so next, let's try this vertex F, okay? So starting from F, we can use this H between F and B to reach this vertex B, and then check whether B is saturated. Okay, so in this case, it is saturated. So we add this vertex E to the set S. Okay. And then let's consider, say, E. Okay. Okay, so from E, we can reach H and I, okay? And both vertices are not saturated. Okay. So actually, there are multiple valid augmenting paths here, okay? Okay, so we can just backtrack this alternating path to find the augmenting path, okay? So this path starting from F, which is not saturated, and then use this H to reach B, and then use this H in the matching to reach E, and finally reach this vertex, which is not saturated, okay? So for this question, there are multiple answers, okay? So this is one of the M augmenting paths. Okay, so the next problem is to find a larger matching using this augmenting path P. Okay. So we just consider edges on this Organomedes path and remove edges that are already in the matching and add all the other edges to our matching. So we were going to remove this vertex, this edge, and add these two edges. Okay. Okay. And next, we have to show that actually this is the best. This is the largest matching. And we're going to prove that this is the largest matching by constructing a vertex cover of the same size as the matching. Okay, so basically all we have to do is to find, again, S and T. And we've shown that if you take the union of T and X minus S, then you'll get a vertex cover. Okay? Okay? Okay, so once again, we start from the unsaturated vertices in X. Okay. Okay, so starting from here, we can add C to the set T, and then add A to S, okay? And then we can consider this vertex F, which is also in S. No, what I just did is to then consider this vertex A, okay? And we can use this H. So we go down to reach B and add this vertex to S, okay? And then we can consider this vertex D, which is in S because it is not saturated, okay? But when we want to further extend the alternating path from this vertex D, all we can do is to reach this vertex, which is already in T, okay? And for this one, yeah, there's no way to further extend it, okay? So this is our S and T. Okay, so according to this property, we can take just these three vertices, okay? Wait. Okay, let's do this slowly, okay? So, because the set I just picked is not a vertex cover, so there must be something wrong. So start from here. This is G, which is not saturated. So we can go down using edges not in the matching to reach C. Okay, and then we can go up using edges in the matching to reach A. Okay, and this finishes the first round. And then we consider this vertex S. All right, because in every round we just pick a vertex, go down and go up. We just do this V shape once. We only consider neighbors of the vertex in S. So we go down. And when we go up, there's only one choice because we must use edges in the matching. So in this case, because G only has this neighbor, so when we go down, we can only choose C. Okay? And we go up, we can add A to the set S. And in the future round, we're going to consider this vertex S. So we count this as a new round. Okay? So then we choose A. Okay, so we can then use this edge, okay, and add B to the set T. And this brings us to this vertex F. Okay. Okay. And so next, let's consider this this edge, this vertex F. Okay, so from here we cannot further extend the augmenting path. But we also have this vertex S because it is not saturated. Okay. So we can go down using edges not in the matching to reach B, but B is already saturated. Okay, B is already in a set T. Yeah, I think my previous S and T are correct. The only problem is that I choose the wrong set. Okay, sorry. So we should pick all the vertices in T. And all the vertices in X, but not in S. So yeah, this is T union X minus S. Okay. So I think previously I chose H and I, which is wrong. Okay. Okay, so this is T, and this is X minus S. Right. Okay. So let's check. Let's check whether this is a vertex cover. Okay. So because we've chosen B and C, so all these vertices, all these edges are covered, and for these two edges, they are covered by the vertex E. So it is a vertex cover, and the size is also 3. Okay, so this this vertex cover shows that our matching, which has a size of 3, is the best. Okay. Because we have a vertex cover of size also 3. Okay. 好，所以我刚刚有弄错一个地方，所以跟大家再更正一下，就我刚刚在选的时候，T 要被选到了 ，OK， 那剩下这两个是不应该去选的，我刚刚选成这两个，所以这是错的。所以你要做的是选 T， 还有不在 S 里面的那个 vertex，OK。Okay, so this is problem 2. So next, Okay, so given this weighted bipartite graph, we have to find the maximum weighted matching. Okay. So the first step is to create the initial vertex cover. Okay. And we can construct the initial vertex cover by just taking the maximum of each row. Okay. So for vertices in Y, the initial weights are just zeros. Okay. And then we can identify all the tight edges. Okay, so for example, this one is tight, and yeah, these 5 edges are tight with respect to this initial vertex cover. Oh, sorry. Okay, so this is the edge between x1 and y5, okay? And this is between x2 and y2, and this is between x3 and y2. So this edge, okay? And the next one is between x4 and y3, okay? So this one. And the last tight edge we've got is between x5 and y2, okay? And so next we try to find the maximum matching, okay? Okay, so these two must be in the maximum matching. So for these 3 edges, we can choose any one of them. So say let's choose this edge. Okay. And the next step is to have more tight edges, okay? And we want to use these tight edges to extend the alternating path, okay? So we have to identify S and T, okay? Okay, so let me do this again. So we start from this unsaturated vertex, x5, and we can then add y2 to the set T, which then leads us to this x3, okay? And we can also add x2 to the set S because x2 is not saturated, okay? And that's it, okay? So we have 3 vertices in S and 1 vertex in T. Okay? So x2, so the second and the third and the 5th row, okay? So these are the vertices in S, and y2, the second column, is also in T, okay? All right, so now we've identified S and T. What we want to do is to try to add some new edge between S and y minus T, okay? okay? So these edges that I just highlighted, they are the potential edges between S and y minus t. Okay. So then we're going to find like the gap, the smallest gap, okay? The gap is the difference between the edge weight and the sum of the vertex weight of the two endpoints, okay? So for example, this edge has a gap of 3 because 8 plus 0 minus 5 is 3, okay? So the gap here is 3, and we want to find the smallest gap. And for this row, the smallest gap is 3. This row, smallest gap is 2. And for this row, smallest gap is 1. So the smallest gap for all these edges are 1, okay? Okay. And then we're going to update the weight for S, okay? So we're going to reduce the weight for S, okay, by 1, okay, so, okay, and for vertex in T, the weight is increased by 1, okay? All right, so after we have these updates, we have one new tight edge. Right? So this edge between x5 and y3 is now tight, okay? So we can add one more edge to our graph, okay? Between, between x5 and y3. Okay. Okay. Okay, and then we just repeat, okay? So let's consider this graph. Try to find the maximum matching, okay? So we can still use the same matching, okay, as the maximum matching, and then we're going to find the two set S and T, okay? And since we've just added this edge between x5 and y3, okay, so we can further extend the alternating path from x5 and can add y3 to the set T. Okay? So as a result, x4 is now in the set S. Okay. Okay, so this is our new sets S and T. And once again, we want to create some new tight edge between S and Y minus T, okay? So let me first highlight these potential edges that we're going to add, okay, between S and Y minus T. So among these edges, we're going to find the smallest gap. For this row, we already have a gap of 1, okay? So once again, epsilon is 1, okay? So if epsilon is 1, then this edge between x3 and y4 will become tight, okay? and also this one, okay? Because it also has a gap of 1, okay? So this will become tight, okay? So in this update, we have 2 new tight edges, okay? But let's first update the weights, okay? So all the vertex weight in S, they are reduced by 1. Okay, and for vertices in T, the weight is increased by 1. Okay. So this is the new weight. Next, let's add these 2 new edges to our graph. So the first one is between x3 and y4. Okay. And the next one is between x5 and y4. Okay. So these 2 are the new edges. Okay. So clearly, after we have these 2 new edges, we have a larger matching because previously this one is not saturated, and X5 is also not saturated. So we can just add this H. Okay. Okay. Okay, so this is our matching, okay? So we're making progress because now the number of edges is 4, okay? But we're not finished yet because we want to have a perfect matching, okay? So once again, let's identify S and T, okay? So now we only have 1 unsaturated vertex in X, okay? Okay, so in this first round, start from this X2, we can add also Y2 in T, and then add X3 to S, okay? So in the next round, we can start from X3. So using this rate edge, which is not in the matching, to reach Y4, okay? And then use the other rate edge, and we can reach X5, okay? Okay, so starting from X5, we don't have to consider Y2 because Y2 is already in T. So all we have to consider is Y3, okay? So Y3 now is in T. So X4, so we can use this edge. So go up from Y3, we can reach X4. So X4 is also in S. Okay. And that's it, okay? Okay, so So next we're going to look at this 8 edges and see which one has the smallest gap. Okay, so all right, so if you consider this edge, the gap is 1. Okay, so once again, the smallest gap is 1. Okay. So this one will become tight. And also this one, okay? Right, okay, because this one also has a gap of 1, okay? Yeah, okay. So let me first add these 2 new edges to the graph. So this one is between x4 and y1. Okay. And okay, so these 2 blue edges are the new edges. Okay. Okay, and then let's update the weight. Okay, so this is our new weight. Okay, so now I think we can have a perfect matching using these tight edges, okay? So we can, let me see. Okay, let me try to draw the augmenting path. Okay, so starting from this vertex, which is not saturated, no, let me see. So I was right? Oh, okay, so let's do this again, okay? Use a different color. So which one should I take next? This one? To reach Y3? Oh, yeah, yeah. Thank you. Well, this is a long augmenting path, okay? So starting from x2, and then y2, and then x3, and then y4, and then x5, and y3, and x4, finally y1. Okay. Okay. So let me first remove the, okay, this one is removed, and this one is also removed, and this one, okay? And we're going to add this edge, this edge, this edge, and this edge, okay? So the first one is between x2 and y2, and the second one is between x3 and y4, followed by x5 and y3, okay? So finally x4 and y1. Okay, so we've chosen these 5 edges, okay? Let's verify whether this is the largest matching, okay? So the total weight, $34, okay? So this is the total matching weight, okay? And then let's consider the total vertex cover weight. Again, 34, okay? Okay, and you can also check whether this is a tight edge. So this one is tight, and this one is also tight because the two endpoints have a vertex weight of 8, okay? And this one is also tight, and 6 is also tight, 5 is also tight, okay? So all these edges are tight with respect to our vertex cover. Okay, so it shows that the matching we have is the maximum weighted matching. Okay, so yeah, let's take a break. Okay. 嘿，请问
这是第一题啦。
第一题，
就我自己的哇，
哎、你的图如果跟我不一样没关系。
哦，因为没有，因为我想说，我记得不是这样子之后，然后要取最大，然后这样排下去，然后去减，这样子去小就好了。就是你找两个嘛，然后剩下的把那个2拿出来，然后剩下2个点去减一这样子。我记得
你说剩下最后刚刚这一步吗？还是哪一步？
就从一开始吧。
哦，从一开始啊、OK， 对。
4选4没错不是吗？
啊，你可以选4，也可以选任何一个都可以。
自己选那个哦。
就关键就是你可以选任何一个，唯一的要注意的就是你在加 H 的时候，你只能加到那些 degree 比较 degree 最大的那些，对，这唯一的限制。All right, so let's continue, okay? So for the next problem, we have to find the dual problem, okay? Okay, so this is our primal problem, and we have to apply the primordial transformation to find the dual problem, okay? But before we even begin this transformation, I want to notice that the last constraint, okay? So you never satisfy the last one and this non-negativity constraint, because if all the variables can only take 0 or positive values, there's no way you can satisfy the last constraint here, okay? So in other words, this problem has no feasible solution, okay? So yeah, so there's no feasible solution. But even though this one has no feasible solution, we can still apply the primordial transformation, okay? And later we're going to see what happens for the dual problem, okay? All right, so first, we create dual variables for every constraint, okay? So since there are 4, we have 4 dual variables, okay? And you can see that some of these signs, they are in red, because I want to stress that this is a little bit strange, because when we discuss primordial transformation, all these inequalities are less than or equal to sign, okay? So before you apply the transformation, we have to first change this sign to less than or equal to. So I guess I'll just change here. So we just multiply -1 to both sides. Okay. And okay, and now we are ready to apply the transformation. Okay, so first, the objective function. The objective function is just the inner product of y and the right-hand side of the constraints. Okay. All right, so this is our objective function. Okay, now the constraint. So we have one constraint for every variable in the primal problem, okay? Okay, so I want to make sure that in our combination, the coefficient of x1 is at least 3. The coefficient for x2 is at least -5. And this is 6, okay? So these are the right-hand side of the constraints. Okay. And then we have to figure out the coefficient of x1 in the weighted combination. So we have okay. So this expression is the coefficient of x1 in the weighted combination of the constraints, okay? So -1 times y1 plus 2 times y2 plus -2 times y3, okay? All right, so this is for x1, and for x2, we have 3y1 plus 3y3 plus 2y4. Okay, 3, and 2. Okay. All right, okay, so for x3, so 5 here, -1 here, and 3 here. Okay. Okay, and finally, all the dual variables must be non-negative. Okay. Yeah, I'm not sure whether this one has a feasible solution or not. Okay. there's no obvious constraint that we cannot satisfy. Right, so this one is easy, okay, because all the values must be non-negative, so we can satisfy this one. And as long as y2 is large enough, we can also satisfy this one. And for this one, yeah, I think we can also satisfy this one. So I think we can make y3 0 and make y2 very large. Okay, see, we can satisfy all the constraints. And for y1, let's make it 0, okay? And for y4, also make it 0, okay? So let's check whether this is a feasible solution, okay? So for the first constraint, yeah, because y1 and y3 are 0, and we have y2 being infinity. So this one is certainly greater than or equal to 3, okay? So the first one is satisfied. And the next one is also satisfied. Actually, as long as y are non-negative, we can satisfy the second one. And the last one, so y3 and y4, they're both 0, and y2 being infinity. So again, we can satisfy this one, okay? So, yeah. Right. Right. So actually, this one has a feasible solution, but we're going to say that this problem is unbounded, because you can. This is a minimization problem, and no. Let me check.下标写错，哪一个？哦，你说这里是不是？那个对，那个是还好。是这个吗？你说写错这还有哪里有写错吗？这样就没问题是什么意思？
因为我刚刚问题是刚刚的地方有矛盾，就是你刚刚那边是写负的嘛，所以我刚刚是说这个 upper bound 会是负值，那这边的 max x1、x2、x3都要大于0，所以这样 upper bound 就有矛盾，因为一个正数要小于等于负数，但是现在改回来更正，就我刚刚的问题就不成立了，这个还是怪怪的，它应该要这个多 transformation 应该要那个。
我晚一点再回来这边 ，OK？ 因为我之前上课前做了准备，跟这个像有一点落差。我们等一下再回来这边，所以dual problem 基本上应该就是这样，应该就没有错了嘛 ，OK？ 所以刚刚的问题是说，如果 primal problem 没有 feasible solution， 那 dual problem 它的形态会是什么 ？OK？ 我还要写错吗？OK， 我再试一次 ，OK。嗨，你说会怎样？OK， 那有可能会到负的无限大吗？现在的问题是有没有可能会到负的无限大？不一定。OK， 等一下我看一下。OK， 所以我要说的是这样，就是我可以把这个 y1 变得无限大，比如说我这边先设100，OK， 所以我设100，然后这边你会看到这边就是负100加，所以我把 y2 设的，这个其实可以不用到那么大，就103，OK。然后加上2倍的103，然后再扣 y3 会是0，OK， 所以只有 y1 跟 y2 不是0，OK。然后 y1 跟 y2 有点像是，我们让它一样大好了 ，OK， 这样比较简单一点。OK， 所以 y1 跟 y2 是一样大，所以第一个 constraint 就可以满足，然后第二个一定可以满足，然后最后一个一定也可以满足，因为 y3 跟 y4 都是0，OK。然后 y2 是正的，所以这个是100，所以这3个一定都可以满足。所以事实上，我可以把这个 y1 换成随便一个数字，比如说 x， 然后这个 x 是一个，你可以想象它是一个很大很大的数字，比如说1000万之类的。那你会发现，你这里的 x 不管多大，它都可以满足所有的限制，而且呢，这个因为 y1 跟 y2 是一样大的 ，OK， 所以这个算出来，这个就会是变得负的很大的数字 ，OK， 所以负500，如果是刚刚的100的话，就是负500加300，所以就负200，OK， 所以刚刚的 arbitrary value 就是负的200，但事实上我可以让它变得更大，比如说我不要设100，我设1000或10000，这个就会变负2000或负2万，所以我要说的是，就这个问题，它就变成是。就我们刚刚说的，就 unbounding， 就是它这个是一个 minimization 的问题 ，OK？ 但是我事实上我这边没有最佳解，因为这最佳解可以到无限小 ，OK？ 无限负的无限大的意思 ，OK？ 所以如果你这边是 infeasible， 所以如果你的 primal 的问题是 infeasible 的话。那你的 dual problem 我记得 dual problem 也有可能是 infeasible， 但是其中一个可能性就是另外一个可能性就是它会是没有最好的 ，OK？ 事实上你可以变成是负无限大或正无限大这样子，因为这边是 minimization 的问题，所以我们想要拿到那个最小，那这边就会变成是它可以到负无限大 ，OK？ 所以你只要把这个，我不要用 x 好了，因为都是重复的。 OK， 所以就不会有一个 upper bound 跑出来，或 lower bound 就都不会 OK， 所以你可以无止境的让它变得很好 OK。对，所以这稍微延伸补充一下，那基本上我们这里就只需要去做那个 dual transformation， 只是刚好这边这一题我的最后一个 constraint 是一个很特殊的 constraint， 会让它根本不会有 feasible solution。那我们在这个 minimization 就可以看得出来说，这个 minimization 事实上你可以无止境，它是一个无底洞，就对了，它可以无限的变小，变得负无限大这样子。OK， 我不知道这样这题有没有问题？所以一个额外的补充。Okay, so the last problem is about the randomized algorithm that we discussed for weighted vertex cover. Okay. Now this is no longer page 120. I think this is yeah. So this one. Okay. No, not this one. Okay. All right. So in this randomized algorithm, we'll consider every edge in this graph sequentially. Okay. So whenever we consider an edge between U and V, we're going to first check whether this one is already covered. Okay. So which means we're going to first check whether any of its endpoints is already chosen. Okay. So if not, then we're going to choose one of these two endpoints according to this probability. Okay. So the probability is like inverse proportional to their weight. Okay. So if this vertex has a large weight, then the probability that we choose this one would be low. Okay. So this is the intuition behind the algorithm. So we've shown that if the graph is a star, okay, so a star means that this is a tree and the height is just 1, okay, and also we assume that the optimal solution chooses the root, okay. So in this case, we've shown that the randomized algorithm has an approximation ratio of 2, okay. So the total weight the algorithm choose will be at most twice the optimal weight. Okay. Right. So so that's why we have to consider this last problem in this homework. Okay. So what happens? For example, say the graph is actually really a star, but the optimal solution chooses the leaves. Or what if the graph is not a star? Okay, we have to consider every possible graph. Okay. Okay, so let's let C star be the optimal solution or the optimal vertex cover. Okay. And let's further assume that in the optimal solution, we choose H vertices in our vertex cover. So what we want to do is to try to reduce the problem or reduce the proof to this case, okay? To the case where the optimal solution choose the root and the graph is just a star, okay? So basically we're going to do this, okay? So this is C star. So this is C1, C2, up to CH, okay? So next we're going to like assign every edge in the graph to one of these vertices in the optimal solution. Okay. So we can think of this process as the following. Okay, so let's assume, for example, yeah, I think this is a vertex cover. Okay, so no. All right. Okay. So now this is a vertex cover. Okay, so every edge has at least one of its endpoints in this C star. So this yellow vertices, they are vertices in C star. Okay. Okay. So next, I'm going to like decompose or partition the edge sets into stars. Okay, because I only know how to analyze stars. Okay. So for every edge, I will just assign it to one of the vertex in C star. Okay, so I'll do this for every edge. Okay. So now I have stars. Okay. Moreover, all the roots are in C star. Okay. So every component here is a star, and the root is chosen by the optimal solution. Okay. Next, we just apply this result. Okay. Sorry, just this result. Okay. So if the graph is a star, and the optimal solution chooses the root, then the expected weight of our solution is at most twice the optimal solution. So that's it. Okay. 所以基本上我们这边做的事情就是把这些 edge 想办法 assign 给不同的 C star 里面的 vertex。OK， 怎么 assign 不重要。OK， 所以比如说像这个 edge，OK， 你可以选底下这个，你也可以选上面那个，都可以。OK， 无所谓。你就随便选一个就对了。所以这样子你就可以建出很多个 star， 然后这些 star 的 root 就会是 optimal solution 选的 vertex， 然后这个 leaf 就会是我们刚刚的 assignment 告诉我们。Okay， 我们之前已经有讲过，这每一个star 我们选到的 total 的 weight expected weight 就不会是超过 root 的2倍，所以这不会超过2倍，这不会超过2倍，每一个都不会超过2倍，所以全部加起来就也不会超过2倍。OK， 好，所以基本上就这样。leaf， 你说，嘿，你说。
前面那个图里面没有写，就是证明那边你没有写到，就是说，如果假如说 root 是100好了，那其他值都是1，
嘿，
那这样的话不是应该选其他值？
哎，没错没错，
这样子的话，
没错，所以我这边的 proof 都是假设，对，OK， 如果譬如说，我们举一个例子，像刚刚那个，比如说今天假设 graph 是长这样子。哎，我知道。就假设他选这样嘛 ，OK， 那一样我们做的事情还是一样，就是我们会去找这个 assignment， 但这一次这个就没什么悬念，就是长这样子。所以这里的每一个 star 就只有一个 leaf。OK， 对，所以这里表面上是一个 star， 但是我们的 proof 就把它拆成4个 star， 然后每个 star 就只有一个 leaf。好，还有问题吗？OK， OK， 如果没有的话，那我们就回到我们上次看的。Perfect matching, okay? But this time in general graph. Okay, so for general graph, we have this Thuse condition, okay? So the basic idea is that if you say remove some set S, okay? So the set S is the set of vertices that you want to remove, okay? So let's remove this S from the whole graph. Then you'll get some components, right? Okay, because we also remove the edges incident to S. So this will possibly create some new components. And some of these components may be odd components, okay? Odd components means the number of vertices is an odd number, okay? For example, 3 vertices or 5 vertices. So whenever you have 3 or 5 vertices in a component, you cannot find a perfect matching using just vertices and edges in that component. You have to use some edges outside the component to create a perfect matching, okay? So for example, in this, suppose we remove this vertex V, we will have 3 odd components, okay? So if we want to have a perfect matching, we have to saturate all these 5 vertices. But since the number of vertices is odd, we have to use at least one edge, okay, which is not in the component to saturate all the vertices here, okay? So basically, we do not want to have too many odd components because this makes the problem difficult because we need to use some edges outside the component to finish the perfect matching. So we want to have some upper bound for the number of components, the number of odd components, okay? So the upper bound turns out to be the number of vertices that we remove, okay? So say we remove just one vertex, then we can only allow one odd component because if you want to saturate all these 3 odd components, you have to use at least 3 vertices outside the 3 components, okay? So, but here, we only remove one vertex, so we'll never saturate all the vertices here, okay? So, we have a notation here, okay? So this O means the number of odd components, okay? So this is the number of odd components after we remove S from the graph. So we do not want to see that this number is too large, okay? So this is called Tude's theorem, says that if the number of odd components is at most the number of vertices that you remove, then it's okay, okay? We can always find a perfect matching, okay? Okay, so last week, we have some warm-up questions. Like, say we have this Tude's condition, okay? So we have a graph, and we already know that this graph satisfies Tude's condition. This means you can remove any set you want. So this S, it can be an empty set, it can be the whole vertex set, it can be a set of 3 or 5 or 4 vertices, okay? You can pick the vertex set, S, okay? But if you want to satisfy Tude's condition, this implies that no matter how you choose this set S, after you remove this S from the graph, the number of odd components is at most the size of S, okay? So you have to, so the key here is that for all, okay? You have to make sure that this inequality holds for every possible set S, okay? Right, okay, so last week we considered a very simple question, that is, if we satisfy this Tude's condition, can we at least show that, well, showing perfect matching perhaps is a little bit too difficult. Let's say, can we prove it, prove that the graph must have an even number of vertices, right? Because if the graph has a perfect matching, then the number of vertices, that is n, must be an even number, okay? So it turns out that yes, okay? So for example, you can replace this S with an empty set, okay? So the number of odd components after you remove an empty set, well, this is just the original number of odd components in the graph. So because it satisfies Tude's condition, so this is at most the size of S. But we do not remove any vertex, so S is 0. So this just shows that the number of odd components is 0, which implies, because if all components are even, then the whole graph must have an even number of vertices. Okay. So yeah, so this is a warm-up question showing that the number of vertices in the graph must be even. Okay. Okay, so then we proceed to prove this by induction. So we're going to use induction on the number of vertices, n, okay? And because we've shown that n must be an even number, so we don't have to consider a case where, say, n is 1, okay? We only have to consider n is 2, n is 4, or n is 6, and so on, okay? So the basis will be n equals 2, okay? So you have 2 vertices, okay? So we want to show that whenever you have 2 vertices and you satisfy Tude's condition, then you must have a perfect matching, okay? So we want to figure out which graph, okay? Because when n is 2, there are 2 possible graphs, okay? This one and this one. And we only have to focus on the one that satisfies Tude's condition. And it turns out that this one, 2 isolated vertices, no edge, this one does not satisfy Tude's condition, okay? Because when you set S to empty set, then you have the number of odd components is 2, because this is one odd component, this is also an odd component, so you have 2 odd components. But this one is too large, okay? Because this one is greater than the number of vertices that you remove. But in this case, S is empty, so this is not less than or equal to 0. So this one does not satisfy Tude's condition. But this one does, okay? So you can check every possible set of any possible S, okay, and you'll see we have the Thieves condition satisfied. Okay. Okay, so good. So now this is the only graph we have to consider when n is 2. So does this graph have a perfect matching? Yes, because you can just take this edge and this will saturate all the vertices. Okay. So this finishes the proof for the basis, okay, induction basis. Okay, so next, the induction hypothesis, okay? So next we assume that the Thieves theorem holds when the number of vertices is less than k, and to show that it also holds when the number of vertices is k, okay? So this is just typical proof of induction. And so below is the high level or basic approach to finish the proof, okay? So we're going to find a very special vertex set C, okay? Yeah. Right, yeah, you can also add the constraint that n must be even. Yeah, this is less than, okay? Yeah. Right, okay, so back to this proof structure, okay? So we want to find a special set C. So this special set C has 4 properties. And among these 4 properties, the most important one is this, okay? So here, what is H? So H is the number of components we create after we remove C from the graph, okay? So recall that in Thieves' theorem, the intuition is like, okay, we want to remove some vertices, okay? This is S, okay? So in this proof, we'll also try to remove some vertex set. But this time, let's call it C, okay? Okay, so after you remove C, you have some components. Let's call these components G1, G2, up to GH. So they are H components. The most important property about this set C is that the number of components here equals the size of C. Okay, so this is the most important property we're going to use. Okay. So this H is the number of components after C is removed. Okay. Okay. And the second property is that actually all these components are odd components. Okay. So G1 is odd, G2 is odd, and so on. Okay. So this is the second property. And the third property says, well, for every component here, you can remove any vertex, okay? I guess let me just draw a bigger picture. Okay, so let's assume that the size of C is 3. So the first property tells us that we have 3 components. Okay. So this set C is like adjacent to these 3 components. Therefore, after you remove this set C, you have these 3 components. Okay. So the third property says for every vertex V, okay, so this is V, this is V, this is V. You can actually remove this V from the component then the remaining graph satisfies Thieves' condition. Okay, so why do we need this property? Because if it satisfies Thieves' condition, then by the induction hypothesis, this one must be smaller than the whole graph, so we can apply the induction hypothesis. Therefore, this one has a perfect matching. Okay? So this is the third property. And I want to stress that this V can be any vertex. Okay? You can remove any vertex from G1, and the remaining graph will satisfy Thieves' condition. So this is quite strong. Okay? And also this holds for the other components, G2 and G3. Okay? All right, so the last property says for any component, we can find a vertex. So let me draw a different graph. Okay, so for any component here, we can find a spatial vertex that's called V1 for G1, V2 for G2, and so on, such that we can find a perfect matching between these spatial vertices in the components and the set C. Okay. So these are the four properties about the graph about this set C. Okay. Now I claim that if you have this spatial set C, you actually finish the proof. Why? Because first of all, we have this matching between the components, the R components, and C. Okay. So these three form a perfect matching. Okay. And how about the other vertices? Okay. Well, we can use the third property to saturate the remaining vertices. Okay. So this is also a perfect matching, and this is by property 3, and this is by property 4. Sorry. Okay. And yeah, and that's it. Okay. Because by the first property here, all the components are odd, so and the number of R components equals the size of C. So really, there's no other components here. I've drawn all the components. Okay, so this is a perfect matching that saturates the whole graph. OK， 所以我很快讲一下，差不多要打钟了。所以，我们等一下做的事情就是要找到这个很特殊的 set C， 然后这个 C 它最重要的特性就是它的大小会跟你把这个 C 从这个 graph 拿掉之后的 components 的个数是一模一样。所以这样这边我画的是有3个 vertex 在 C 里面，然后把它拿掉之后，它就真的会有3个 components， 而且这3个 components 都会是 odd components。OK， 那因为它是 odd components， 所以直觉上来讲，它就会多一个出来。OK， 那多一个出来，我们要怎么 saturate？ 就是第3个这里的 property， 它就会说，不管你可以选任何一个 vertex 把它拿掉，那剩下的它都会满足 Hughes condition。所以它就会有 perfect matching，OK？、所以就是我上面这边画的这些蓝色的在 R components 里面的，这些都会存在，因为它们会满足 Hughes condition， 所以它们就有 perfect matching，OK？、那所以剩下的要 saturate 的就是这种我刚刚选出来的，还有 C， 那这些它也会有一个 perfect matching， 就因为刚刚的第4个 property。OK， 所以就每一个这个 odd components， 我都可以找到一个特殊的这个 V1、V2、V3， 然后它们刚好可以跟这个 C 是被 match 在一起。OK， 所以这样子我就可以找到这整个 perfect matching， 所以就会结束。OK， 好，所以等一下我们会看的就是到底这个 C 要怎么建。OK， 好，所以我们先下课。
第一堂课没有来
OK，
然后就是作业的第3题，还是有点不懂。
好，没问题。第3题。
对，我有回去看投影片，但是我忘记
好，没问题，没问题。
我看一
下。OK， 第3题 OK。嘿，好。不，第一个这个应该不是第一周上课的内容啊。
对，我说我回去看投影片。
OK。
就是老师那个步骤。
好。
回想。
了解。好，没问题。那在最前面。OK， 所以这里嘛。所以有比较明确是哪一个步骤，不知道为什么要这样做吗？
我知道，就是要先找最大的数字，然后老师会写在旁边。
对。
然后左边是 S， 上面是 T 嘛。
对。
然后
不，应该说左边是 X， 上面是 Y。
X 跟 Y。
对。
然后我记得就是上面的一开始都是0。
上面的一开始都是0。对，没错。
对。然后就是老师的投影片有一个是就是圈那个方方的框框，然后在 min gap 那边忘记确切的步骤。
OK， 所以您说要怎么找到那个最小的 gap 嘛？
对。
OK。
然后跟那个方框该怎么圈
？OK， 好。好 ，maybe 看这里好了，所以我看一下哦。我们1、2、3、4、5嘛，所以这5个 edge 就是最一开始的那5个 tight edge。OK， 然后我们找到 tight edge 之后，我们接下来会做的事情就是去找 maximum matching。所以就是上面荧光笔画的这3条，就是一个 maximum matching。好，那接着我们会做的事情是，当然会先去检查这个 maximum matching 是不是就是 perfect matching， 因为如果就是 perfect matching， 那就结束了，对。所以在这个 case 它不是 perfect matching， 所以我们就要想办法让它变大。那要怎么变大呢？就是我们要去找 augmenting path。OK， 就跟第一题那个一样 ，augmenting path。那你要怎么找 augmenting path？ 就一定会是想办法从 S 再走到某一个目前不在 T 的点。
对。
因为如果 S 可以走 S 所有介于 S 到 T 的我都已经加进去，我现在想要做的是想办法把，譬如说这个 X3好了，想办法把它，譬如说能不能连到 Y3， 或X3能不能连到 Y4？因为这个就是目前不在 T 里面的。
对。
所以如果可以延长，我就可以让 alternating path 变长。alternating path 变长，我就有机会找到一个 augmenting path。对，就有机会找到更大的 matching。所以我要想办法做的事情，就是要想办法让某一些介于 S 跟 Y 减 T 的边让它变成 tight。OK， 所以我刚刚做的事情就是先把 S 找出来，所以就这3个，还有 T 找出来 ，T 就只有这个。那这个 S 跟 T 怎么建，你知道吗？这个应该是第一题的部分。所以我们会先从 unsaturated 的 vertex 从这边就是 X5走下来嘛。然后 alternating path， 所以它接下来就一定会走 matching 的 edge。对，所以那 anyway 这个一定会加进去 T 里面，它会加上来，所以它就会加到 S 里面。然后再从这个点出发，可是这个点出发就基本上没路可以走了，因为我们要往下，接下来要往下走就是只能走没有在 matching 那边，所以这个就不用。那这个是一定也会加进去，因为它是 unsaturated， 所以这个也会是 S， 然后走下来，但这个刚好已经加进去了，所以就这3个就是在 S， 这个是在 T。
我觉得我还是有点卡住，我可以理解我们现在有3条荧光笔的，已经先是 augmenting path 了，对吗？
不是，这3条荧光笔是 maximum matching。OK。对。
然后我们现在想要找 augmenting path，
对，
加到 matching 里面，让它变得更大。
可以这么说，对。
好，然后。
所以我刚刚说最关键的就是要想办法让。就是要让介于 S 到 Y 减 T 的，让它变成 tight。比如说我们马后炮直接看一下，我们刚刚选出来的，我猜应该是荧光笔这一条 ，X5到 Y3这一条。对，所以如果是这一条的话，你看，如果我可以把它加上去的话，那我就可以延伸我的 alternating path，因为我就可以多一条这一条出来。这条一样不是 augmenting path 啊，它还不是，但是至少变长了。对，所以我们的目标就是去找到这样子的 edge， 可以把它加进去。所以我刚刚这个红色框框怎么框的？就是我是去框所有 S， 就是所有的 S 跟不在 T 里面的。所以就是这几个，所以我才去圈刚刚这些红色的 edge。因为这些 edge 就是还没有 tight， 那我要想办法让它变成 tight。那我要怎么让它变成 tight？ 就是我会去 update 这里的 S 跟 T 的 weight， 让 S 的变小 ，Y 的变大，T 的变大。对，所以我就会去看哪一个 edge 它的 gap 是最小的。那刚刚看出来就是这个，因为它的 gap 就是还没有 update 之前就是60减掉5，所以就是1，所以我就可以让这个6变成5。那这样这个就会变 tight， 我就可以把它加上去。
好，我回去想一下。
对。
但我可以再回头问一个问题。
可以啊，可以。
就老师怎么知道一开始的 matching 是圈这3条？
哦。
比方说我自己写的时候，我可能就会选8、8、9、8、6，就变成有5条了。
吗？可以再说一次。
就是
为什么有5条？
我可能就把每一行，我以为是每一行找最大的嘛。
是没错啊，就是绿色的这5条。
对。然后我可能就会，比如说我就会有Y5到 X1的，X1到 Y5的，然后 X2到 Y2的，X3到 Y2的，X4到 Y3，然后 X5到 Y2的5条边。
对，没错，就这5条。
对，我以为是这样。
可是这5条不会是一个 matching。
哦，因为有重叠
对，
的。
因为这5条，因为他们这样这3条 ，X， 对啊，所以这不是 matching， 对。
我漏了这一点。
所以 matching 的边一定是他们不能碰在一起。
OK。然后，那我还可以再问一下第10题，就是那个转成 dual problem 那里。
OK。
然后那边我后来有去找一些资料。
对。然
后我这边有一个疑问是，我
发现就是它好像有一个强对偶性嘛。
是没错没错。
就是在
我们没有讲强对偶性，我们是讲弱，就是 weak duality，我们没有讲 strong。
然后我到那边就是看的时候，它好像可以把一些条件再变得更 tight 一点，就变成可以加入变成等号。我们现在好像都是大于等于。
那其实是一样的，就是那个只是表示的方式不一样，就是你会看到有时候都是等号。那这个也可以做到等号，就是你可以，但是你必须要加一些 variable 进去啊。那个不重要，那个我认为不重要，就是至少在我们这门课不重要了。
OK。
就是我们要看的就是我们的动机很简单，就只有我们那时候怎么从 matching 得到 verse cover，我们就透过这种 prime module 的转换，把 matching 转成 verse cover。这也是我唯一想要讲的东西啦。对，那就是 prime module 它有很多特性，譬如说你刚刚讲的 duality， 对吧 ？strong duality 这样子。对，它还有一些其他特性，但是跟这门课就没有太直接的关系，所以我就没有特别讲这样子。对但你说的是对，就是有时候你会看到那个形式都是等号。对但是
就没关系，
都是等价的，就是有了考虑多这个等号不会让你有特别厉害的东西。
OK， 好，
对，OK， 好。All right, so let's discuss how to create this special set C, okay? So in the following, you only need to find such a vertex set C, which satisfies these 4 properties. As long as we have this set C, the proof is complete, okay? Okay, so recall that I say the most important property is that the size of C equals the number of components after we remove C from the graph, okay? So this is property 2. Or okay. So let's first focus on this property, okay? So I claim that we can always satisfy this property, okay? And this set C is non-empty, okay? So how to do this, okay? So we have a graph. Okay, like this. And I claim that we can always find a special set C such that after you remove this C, the number of components you create equals the number of vertices that you remove. OK， 所以我先把问题稍微简化一点 ，OK。所以这接下来大家应该都可以 follow，OK。所以如果你刚刚听不懂前面的也无所谓，现在是一个全新的开始 ，OK。我们现在要做的事情是给你一个 graph，OK， 像我下面画这个 graph。那我想要说的事情是，你一定有办法找到一个 set， 那这个 set 第一个它不是空的 ，OK， 所以一定有一些点在里面。那你把这个 set 拿掉之后，剩下的 components 的个数一定就会跟你拿掉的 vertex 的个数是一样的。所以你可以看得出来要怎么拿这里的 vertex 才可以让剩下的 components 等于你拿掉的 vertex。OK， 哪一个？如果是这个 graph 可能是这样子，但是OK， 没错。这确实它有一个专有名词，那个专有名词叫 cut vertex。OK， 不过专有名词不是很重要，反正就是我要确保说，我拿掉那一个点之后，整个 graph 一样是 connected。因为我就只拿掉一个嘛，所以我的目标就是 components 就会是一个，所以你就不能说，我拿掉一个 vertex 之后，突然间变很多 components， 所以我就不行。OK， 所以以这个图为例的话，这个。它就叫做 cut vertex， 你把它删掉之后，就会有2个 components 跑出来 ，OK？ 所以，但是如果你移的不是这种 cut vertex， 那像另外一个这个也是 cut vertex。所以这2个你不能移，那其他的你都可以，因为其他的你移掉之后，这整个 graph 一样会是 connected。Okay, so all we have to do is to remove any vertex that is not a cut vertex. Okay, so if you remove any vertex that is not a cut vertex, the number of components you get is 1. Okay, because you cannot create more components. Okay, so now we know that we can at least satisfy this property too. Okay, and since we know that this set C must exist, we will take the largest such set. Okay? So the set C is the largest set that satisfies property 2. Okay? So there are multiple ways of creating this set C. We will choose the largest set C. Okay? And that's it. So that's how we create the set C. Okay? So next we're going to show that this set C satisfies the first property, that is, all the components that you get from removing C from the graph will be odd components. Okay? Okay, so let me draw the picture. Okay, so this is set C. Okay, so these are the components we get after remove C. And because the size of C is 4, so we get 4 components. Okay. So next I want to argue that all these components must be odd components. Okay. So what happens if some of these components are even components? Say this G4 is just a square, okay? A cycle of length 4. So we are looking for some contradiction, okay? Yeah, why? No, but we can also have another G5, okay? And then, no. No. Okay, like this, okay. Yeah. So we can have some we can have some even components here, but still the number of vertices is even, okay? So this is not the contradiction. So really the other property we have now is that C is the largest set that satisfies the second property. That is, the number of components we get equals the size of C. So we want to find some contradiction related to this property too. OK， 所以我们现在要说的是，这个 C 基本上我们就已经决定好了。OK，C 就是那个最大的 set。那怎样最大呢？就是删掉这些点之后的 components 的个数，刚好会等于删掉的点的个数。OK， 再说一次，你删掉之后，你会有一些 components 跑出来，这些 components 的个数刚好要等于你删掉的点的个数，所以很多 set 都会满足这样的 property。OK， 至少我们刚刚看到的一个就是这个。OK， 只要比如说你删掉一个点，只要这个点不是 cut vertex， 你得到的 components 的个数就会是你删掉的点的个数。当然在这个例子刚好都是1。OK， 那我们这边要看的是就最大的那一个。OK， 有可能会你可以删掉2个、删掉3个、删掉4个，或删掉10个都可以。我们要看那个最大的。OK， 所以这边画的就是这个最大的这个set， 那这个 set 就是它的 size 就会等于它的 components 的个数。OK， 好，我现在要说的是，那剩下的就是这些 components 一定每一个都是 odd components， 它不会有 even components 在里面。OK， 所以我现在这边画就是有2个 even components 在这里。那我要问的就是有没有什么矛盾 ？OK， 因为我们想要说明的是不会有 even components， 所以如果有 even components， 那铁定是哪里会怪怪的。所以看有没有人可以看出来它怪怪的地方在哪里。Okay, make it even simpler. Okay, so these are 2 odd components. Okay. So I'll give you a hint. Okay, so if you have this odd component, sorry, this even components, and actually you can have a larger set C. So this will be a contradiction because you just claim that this is the largest set that satisfies this property 2. But I claim that if you have even components, then you can have a larger set C that satisfies property 2. So how to create this larger set C? 们要想办法找到一个更大的 set C， 然后这个 C 就是满足刚刚的条件，就是 C 的大小就会等于你把它删掉之后，点的R components 的个数，不 the components 的个数。对，我好像有弄错一个什么东西，等一下哦。OK， 所以我要更正一个地方。我刚刚说这个最重要的 property 是我们把 C 拿掉之后，这里的 components 的个数，就是不管是 even 还是 odd， 这里的 components 的个数跟 C 的大小是一样的 ，OK？ 我这边可能我需要做一个更正，就是我这边要只看的是 odd components，OK？ 所以，OK， 抱歉 ，OK， 所以这个应该是只去看 odd components 的个数 ，OK。所以如果是你只有满足刚刚第二个 property 的话，确实它就有可能会有一些 even components 在这里。OK， 但是第二个 property 它只是说的是你把这个 C 删掉之后，你的 odd components 的个数会跟 C 的大小是一样的。OK， 所以我们再 go through 过一下刚刚 这里的 proof，OK，、好，所以刚刚的第二个 property 会告诉我们说 R components 的个数会等于 C 的大小，但第一个 property 又告诉我们说，哎，它其实不会有 even component， 就是这里 ，OK， 对，其实不会有 even component， 所以刚刚这些假设就是我们会有 even component 是不可能出现 ，OK， 所以换句话说，我们刚刚的图画的是对的，但是我们刚刚逻辑有一些问题 ，OK。所以一样就是这个没有其他的 components 的原因，就是因为就一样 ，OK， 所以上面的这些 components，R components 的个数就会是 C 的个数 ，C 的大小，但不会有 even component， 所以我们就已经考虑所有的 components。OK， 所以不好意思跟大家做这个更正。那所以这边我们就一定要去考虑这个。OK， 所以这是我们的第二个 property。那 proof 是一模一样的，因为你一样还是可以拿掉这种 non-empty 的不就是拿掉这种不是 cut vertex 的点 ，OK， 那一样你就会产生一个 odd component，OK， 因为本来的 graph。我们在一开始上礼拜的 warm up 就已经告诉我们，这每一个都会是 even component。OK， 如果你满足 Till's condition 的话，每一个 component 都会是 even。OK， 然后我们这边做的事情是去证明说，哎，真的有这种特殊的 set C， 你把它拿掉之后，你的 R components 的个数会跟 C 是一样大的。OK， 所以我们做的事情就是去删掉其中的某一个点。OK， 既然它不是 cut vertex， 你把它删掉 ，even 扣掉一个就会变 odd， 所以这一个删掉之后，这里就会变成有一个 odd component 跑出来。OK， 所以这个就会是正确的。OK， 好，然后接下来我们再去看满足这个 property 2里面最大的那个 set。OK， 所以假设这个是 C 这样子。OK， 所以我们再回到这边。OK， 所以这边就会告诉我们说，我们想要说明的就是这个 C 它一定会满足第一个 property。就是其他的 components 都不可能是就不会有 even components， 所以这个图画的会变这样子。所以假设 C 里面有4个，所以它就会有4个 odd components， 所以这些都是 odd。OK， 那我们假设说，还有另外一个 even component， 所以你把 C 删掉之后会跑出来的。当然也有可能说，它一开始就跟 C 没有连在一起，它自己就是一个 component， 这也有可能。OK， 那我们接下来要说的就是这个有矛盾 ，OK？ Right, so now this proof becomes much easier than the previous one. Okay, so all we have to do is to add again some non-cut vertex. To the set C, then we can get a larger set C, which satisfies property 2. So just proof by contradiction. So assume there's an even component after we remove C. And then we can choose any non-cut vertex. And we can add this vertex to our set C, which will create a larger set, which also satisfies property 2. So that's a contradiction because we assume that C is the largest one. Okay, so this is the proof for property 1. So next, we'll prove that we can satisfy property 3. Okay, so this is the set C, which is the largest set that satisfies property 2. And we have some odd component here, Gi. Okay? And we want to prove that we can choose any vertex V in this Gi, then the remaining graph will satisfy Thieus condition. Okay, so this is property 3. Okay. So to prove this, we will prove by contradiction. Okay, so now the problem is if this graph, this blue graph we obtain by removing V from Gi, if this one does not satisfy Thieus condition, then what does this imply? Okay. So if a graph does not satisfy Thieus condition, this means we can find a set S such that after you remove S, you have many, many odd components. The number of odd components you have is greater than the size of S. Okay? So this is what happens if a graph does not satisfy Thieus condition. So this implies that there's a set S such that the number of odd components you get by removing S from the graph so this is greater than the size of S. Okay, so this is what happens if a graph, in particular this blue graph, we obtain by removing V from Gi. Okay, so we further remove S from the graph, then the number of odd components will exceed the number or the size of S. Okay. 所以这边有点绕 ，OK， 就是因为我们接下来要说的就是这个每一个 odd component Gi， 你把随便一个 vertex V 拿掉 ，OK， 所以这个 V 可以是任何一个 vertex。大家应该也可以看出来为什么要是任何一个 vertex， 因为我们在第4个 property 我们就会想办法 每一个 GI 都找到一个 vertex 跟 C match 在一起，所以我们这边要可以让所有的 vertex 我都可以删掉一个，剩下都可以找到一个 perfect matching， 所以我要去说剩下的这个就是 GI 减 V 这个 graph， 它会满足 Till's condition， 那这样它就有 perfect matching，OK，、所以我们要说的是，假设它没有满足 Till's condition， 那我们就要想办法找到矛盾 ，OK。这边如果你没有满足 Till's condition 的话，就代表说，你可以找到一个 set S， 这个 S 呢，你把它拿掉之后会有很多的 odd components， 所以就这个数字就会很大 ，OK， 这就是你拿掉 S 之后的 odd components 的个数，这个会很大，多大呢？会比你拿掉的这个 S 来的更大，所以这样就违反 Till's condition。那我们接下来就要从这边出发，然后去找到一些矛盾的地方。OK。Okay, so to find a contradiction, I claim that actually if you have this result, then we can have a larger set C. Okay, a larger set that satisfies the key property, the property 2. Okay. So what is this larger set? So this is our larger set. Okay. So we will further add this vertex V and the set S. So this will form a larger set. Okay. And then we're going to show that if you have this result, then we can also satisfy property 2. Okay, so that's a contradiction. Okay. 所以我们这边的 contradiction 比较稍微复杂一点，就是我们会说，如果你有找到这个很特殊的违反 Till's condition 的 set S， 那我们可以做的事情是，我们其实就可以找到一个更大的 set C， 这个 C 就可以一样满足刚刚的第二个 property， 就是你把 C 删掉之后 ，odd components 的个数会等于 C 的大小。OK， 所以只要有这个就矛盾了 ，OK， 所以我们等一下要做的事情就是想办法去说，刚刚我画的这个。Okay, so the goal is to show that the size of this set equals the number of odd components we get after we remove this set from the graph. Okay. Okay. Perhaps let's call C prime. So this set is C prime, so we want to show that the size of C prime is the number of odd components we get after we remove C prime from the graph. Okay. Okay. All right, so because the whole graph satisfies Thieves condition, okay? So we have this inequality. Okay, so this is because the whole graph satisfies Thieves condition, okay? So if you remove a set from the graph, then the number of arc components cannot be too high. It is at most the size of the set that you remove, okay? OK， 所以这边我慢慢讲 ，OK， 其实整个 proof 没有很长，但是就是有几个关键会需要稍微解释一下。所以这边我们说的事情是回忆一下什么是 Thieves condition。Thieves condition 指的就是你可以从这个 graph 拿掉任何一个 set， 任何一个，那拿掉之后你会有一些 arc components， 那这 arc components 一定不会太多，它最多就跟你拿掉的 set 是一样。所以我们这边做的事情就是，那我就拿掉这个 set， 就是我们刚才那个 C prime，OK， 所以因为它满足 Thieves condition， 所以你拿掉 C prime 之后 ，R components 的个数最多就是 C prime 的大小 ，OK， 所以这很单纯，就是因为具有满足 Thieves condition。OK， 所以因为这是一个等号嘛，所以我们唯一接下来要做的就是这另外一个方向。OK， 好，所以我们只要搞定这个就这个就结束了。好，所以这个是我们刚刚有的，我会把它贴过来，让大家比较一下。OK， 所以蓝色的是已经我们有的 ，OK， 然后我们要说，事实上红色这个也会成立这样子。所以我们先找到这个红色的跟蓝色它们之间的关系 ，OK。OK， 所以这是我们接下来的目标。OK， 然后我们已经知道下面这个东西。OK， 所以我画一下图，这样大家会比较好理解一点。所以这是整个 C 然后你有 GI 在这边，你可能有 G2、G3，OK， 所以就画3个就好。好，所以我稍微把上面的这个每一个符号跟大家用这个图解释一下 ，OK， 这样大家比较有感觉。所以第一个，我们先来看一下红色这个，红色这一串是什么？就是你把整个 graph 拿掉 C， 拿掉 S， 拿掉 V 之后的 arc components 的个数 ，OK。所以换句话说，你可能这些蓝色的这3个蓝色的就是你把 S 跟 V 拿掉之后会产生出来的 R components。OK。好，所以以这个例子来讲的话，这个数字就会是3加2 ，OK， 对，就这3个，然后再加这2个，因为这2个一定会是 R component， 是这个我们刚刚第2个 property 就已经讲了 ，OK， 第一个跟第2个就会告诉我们剩下的这 components 都会是 R 的。OK， 所以所以我这边这个我们刚刚说的就是这些蓝色的 R components， 这些就是你把 C 删掉之后，又再另外删掉 V 跟 S 得到的新的，那这个就会是对应到这3个。OK， 所以这是 GI， 然后扣掉 V， 再扣掉 S 的。然后剩下的这一项就是对应到这里，就是你把 C 拿掉之后的 R components 的个数，再减1，因为减1是因为这个你就没有算到了 ，OK， 所以这个减1是因为我们 GI 就排除在外，所以就有这个减1。OK， 所以你会看到蓝色这一项就是都是一样的，所以这个就会是OK， 然后 OK， 决定还是看一下我的。好，我决定我要发了我的笔记 ，OK， OK， 所以我这边第一步我会做的事情是，让 C 的大小就是 H，OK， 那所以这一项。OK， 所以这一项就会是因为 C 的大小是 H， 所以这一项就会是 H 再加上 S 的大小，再加上1，OK， 就是V 他自己一个人，所以就有加1。OK， 然后看左边 ，OK， 那左边呢？左边就是刚刚这一项，就这一项 ，OK。所以这一项我们刚刚已经看出来，就是绿色这一项就是 H 减1 ，OK， 因为我们刚刚说你 R components 的个数就会是跟 C 的大小是一样的所以这边就是 R components 的个数减1，所以就会是 H 减1。OK， 所以就是刚刚这一项。OK， 好，因为时间到，不好意思，我刚刚应该一开始就要发了我的笔记 ，OK， 所以我们这个就下次上课再讲 ，OK， 不好意思。那所以下礼拜我们会有考试，然后考试基本上就会考到，当然这个 test condition 就不在里面 ，OK， 所以我们就考到我们刚刚整个作业讲解完的地方，然后再提醒大家一下，就是不能上网。考试的时候不能上网，当然你可以带任何的笔记的资料 ，OK， 书也可以，教科书都可以。 但是不能带电子设备，像电脑或手机等等。OK， 好，所以这个我下次上课我们再继续。